Thank you, Pierre, and good evening, good afternoon, everyone. So this last presentation, I will go over one of our experimental proof of concepts that we developed at Thales IMS in order to investigate the use of artificial intelligence in a rather safety-critical application, the resolution of midterm conflicts. So I will begin by going over what exists today in ATC systems, so conflict detection, and how our resolution advisory function is going to work in our upcoming systems, so in the next years. And then I will go further into the future in order to investigate what can we achieve with AI, is there anything to gain by using AI, and how would we do it? How would we answer questions such as safety, in this case where we have more or less zero tolerance for errors, and how would we integrate with an existing system, and how would we build such a network? So, as most of you know, today's systems are capable of predicting trajectories based on flight plans. So most commercial aircrafts are going to fly a flight plan of a series of geographical points. And the ATC system, using physics and classical algorithms, also the performance of different types of aircrafts, is going to be able to predict a relatively accurate trajectory for the aircraft, as long as the aircraft is going to follow his planned route. And once we have these trajectories, then we can start looking at conflicts. And what I mean by conflicts is loss of separation. So there are modules in today's systems that are going to analyze all the trajectories that are inside the system right now, and they are going to identify if at any point in the next 20 minutes, two aircrafts are going to come closer to one another than 5 nautical miles in general, and 1,000 feet vertical separation. And once we identify a conflict, this is where the air traffic control operator needs to step in and identify a new trajectory, so provide the pilot with some information in order to change his trajectory and avoid this conflict, while at the same time avoiding conflicts with every other aircraft in the space. So when air traffic is very dense, this can be quite stressful, and it can put a lot of pressure on the operator. So for this reason, we've built an automatic resolver in our system today that's going to search in the background for an alternate trajectory that is acceptable, like you see in the image, for example, the dotted blue line over there. This is just direct to another point of the trajectory. And once this is found, the operator can be informed about its existence, and he can decide to use it and implement it with a single click, or he can decide to do something else. So this is just an advisory function. So what it looks like, you can see in this image, where on the bottom left you have the card window for the operator, where he can see all the detected conflicts in his airspace. And you can see a light bulb associated with each one, which indicates that the system has an automatic resolution. So if he wants to look into more details, he can look at the trajectories of the aircraft, and the system is going to show him this little blue line over here, which is an alternative trajectory that was found by the system. And if he decides to use it at any point, he can click, implement it in the system, and he has the certainty that this is a viable route that's not going to create another conflict. So the difficult part here, as you can imagine, is how do we find this trajectory? If we just consider a lateral resolution, for example, where we want the aircraft to continue on a different heading for a certain distance or time, and then we want it to go back to its original trajectory, then just this simple approach is going to create thousands upon thousands of different options, as you can see on the image on the right. And furthermore, if we complicate the problem and we consider also vertical resolutions, so change the altitude of the aircraft and then for a certain duration and then tell it to go back to its cruising altitude, then we are talking about hundreds of options, and we also need to take into account airspace constraints. We cannot use any altitude we want, and we can complicate it further and take into account a reduction in speed. So in today's system, in order to find the best candidates to solve a conflict, we are using what was referred to today as symbolic AI and knowledge-based systems and classical tree search algorithms. So we are pruning all the options and we are continuously searching in the background for the best alternative. Once we find it, then we also have the possibility to validate it by creating a validation loop inside the system before the operator is even aware of its existence. And once it's validated, it's safe, and we are sure that this will not create another conflict, then we can propose it to the operator. So what are the limitations here? Well, they mainly come from computational power limits. And what I mean by this is we simply cannot analyze every single option in the background. It's going to take too much time. It may take several seconds to even find the first option. And sometimes we can miss other solutions. And obviously, if you want to chain multiple solutions, well, in that case, our combinatorial problem is going to explode and things will be very, very difficult and costly. So what we've done until now works pretty well. So why look further? Well, we've all seen today and in general that artificial intelligence has shown a lot of promise in many, many different fields. And we also know that once it learns, we can run the inference process very fast. So this will enable us to run multiple resolutions ideally. And furthermore, it can open the door to new features into the system, such as global traffic optimization or complex solutions that are going to chain multiple clearances in order to achieve an even more optimal trajectory for an aircraft. And there are some other advantages. We can automatically learn, and we can also transfer the same approach, for example, to different use cases. So what AI technology can respond to this type of needs? Well, we found that deep reinforcement learning provides a solution to this, precisely for its capacity to predict what is the impact in an environment of an action. So if we take an action, we want to know how this action is going to be impacting the end result in a certain environment. And of course, there are limitations to this. So it's very difficult to develop a reinforcement learning system. We need to make sure we align the development of the model with the actual system. We need a simulator. And there are also safety concerns, that as it was mentioned in several other presentations. So even if we manage to achieve a 99% accuracy, this is still not acceptable. We cannot afford 1% of the time for the system to fail. So to address this, we decided to go with a hybrid approach and to combine the two approaches. What I mean by this is, if we have a conflict and we have a number of options that we can make, what we want the network to do actually is to tell us what it thinks about each option with respect to a certain cost function. So rewards and penalties for good actions and bad actions. And if we can obtain this with a network and have a vector like you see at the bottom that can tell us this heading is better than the other one, and this range of angles are better than the other one, then we can use this in order to accelerate the search in our classical algorithm. So we no longer need to explore the entire space. We can focus the search, or we can even pick the best solution out of this. And once we do this, we can use the classical approach in order to validate this solution and make sure it's still valid. There are no conflicts, and everything will work once we apply it. Since I mentioned cost functions, well, we had several ideas. Of course, since this is an experimental project, it's not yet finalized, so we are still thinking about what else we could consider, but obviously we need to aggregate multiple criteria. So we need to make sure we are not creating new conflicts. We need to make sure we are solving the conflict we are trying to solve. We need, well, not need, but ideally we would like to have a shorter trajectory. We would like to minimize the fuel consumption. And we can also take into account more complex metrics, for example, such as concrete creation probability. So what I mean by this is if we are able to model based on meteorological data, what is the probability of creating a concrete? And for this, we found the Schmidt-Appelman criterion very useful. Then we can simply quantize the space and add a cost to the trajectory for traversing each one of these cells, which will give us a metric of how good this trajectory is with respect to concrete creation. And we can compare it with different options. And the beauty of using reinforcement learning is that we don't need to compute all of this all the time. We only need to compute it in training, not in inference. So how did we address the first pain point, I would say, the development of such a model? Well, as most artificial intelligence projects, we begin with historical data. And unfortunately, it's very, very difficult to find proper resolution data from human operators and very large databases. So that's why we started with simple trajectories historically, and we've created tens of thousands of 20-minute scenarios up to 30 minutes. And fortunately, well, unfortunately for us, we didn't find any conflict. So that means the air traffic control operators are doing a great job, so no loss of separation. So we were forced to augment this data a little bit in order to create some artificial conflicts, which still resemble the reality, and they are feasible and possible in that airspace. Once we have this, then we had to build two other components. So an AI training component containing the neural network and a simulator that is aligned with the system. So what I mean by this is that we want the simulator to behave exactly like the system where we are going to deploy this model. The two need to be aligned. So the way it works is we create a loop where the simulator is going to load a simulation scenario, and then it's going to play the simulation. Once a conflict is detected, then it's going to ask the neural network, give me a solution, tell me what to do. The neural network is going to start as a completely random model that's going to propose whatever. And the simulator is going to take that, implement it, adjust the course of the aircraft, and compute all of these cost functions and provide this feedback to the training module. The training module is going to memorize all of these experiences, and of course is going to prioritize experience that is especially failures more than successes, since we want to learn from failures. And periodically it's going to update the neural network model in order to maximize this cost function and to maximize the feedback that it's receiving from the environment. So we've ran this system for several days, and we noticed that after about 10 million, 15 million clearances and tests, the network began to understand and to actually maximize the cost functions that we provided. And after about 20 million clearances, we actually found that the network was beginning to solve about over 99% of the conflicts in the airspace. And not only it was solving the conflicts, but it was actually, on average, reducing the total length of the trajectories and reducing the fuel flow. So once we have this neural network, we need to address the second pain point, and that is, what do we do with it? How do we integrate it into the system? And what do we do with that 1%? We cannot tell the operator one of the 100 solutions may result in a loss of separation. This is not acceptable, not at all. So You have here a very schematic representation of an ATC system and the main components that are involved in this integration. So the way it works is the MTCD module, so the midterm conflict detection module, is going to identify a conflict. Once this conflict is identified, then the resolution orchestrator is going to begin looking for a solution, and in this case is going to start looking for a solution using the neural network. It's going to ask the neural network, what do you think, what are the best options? From these candidates, he is going to take the best one and begin a validation loop. He's going to use the flight data processing module in order to predict the trajectory that would result if we were to apply this solution. And with the new trajectory, the alternative trajectory, he's going to ask the MTCD module, is this trajectory acceptable in the environment right now? So since the trajectory is validated by a certified component, the MTCD module, and the probe function can also be used by a human operator, at this point we can say that we believe it is acceptable as a solution. So only at this time we are going to propose it to the human operator on the screen, and as always the human is going to be the last validation step, because he can always reject it, or he can accept it if he believes it's a pertinent solution. Okay, so to conclude the presentation, I will leave you with a small video summarizing this project and containing some real footage from the tests that we performed with the neural network integrated with actual industrial components on an airport. And the scenarios that you see here were scenarios that were designed by air traffic control operators, so they were completely new and never used in training, and quite challenging. Some of them were designed for Cesar. So some of the scenarios were designed for Cesar exercises in order to create challenging situations for operators. And what I can tell you is that we were quite surprised to see that every single solution that came out of the neural network in all scenarios was acceptable, and it passed the validation test with the MTCD module. And once we applied these solutions in the environment, the conflict was solved, and it didn't lead to the creation of Okay, so thank you very much.